Hi everyone, welcome back to my channel. This is Dr. Spinach. This is the third video on distribution of drug in the series of pharmacokinetics. We are very well familiar about the pharmacokinetic acronym ADME, wherein we have completed with absorption of the drug. Now it's time that we move forward to know how the drug is distributed in the body. Hence, I'd highly recommend you to go through these tutorials to get a better understanding of the subject. Beginning with distribution. After the drug gets absorbed into the bloodstream, it gets distributed to other body tissues and organs that initially had no drug until the equilibrium is maintained. This drug that's distributed in the body is measured by VD, that is the volume of distribution. The formula for which is dose administered by any route upon the plasma concentration achieved.
So, how to find out the plasma concentration of a drug?
Let's understand this by an example. We took a beaker filled with 5 liters of water. Then we added 100 mg of a drug into the beaker. The plasma concentration achieved would be 100 divided by 5, that is 20 mg per liter. And the volume of distribution would be the drug administered upon the plasma concentration achieved. So here, the drug administered is 100 mg and the plasma concentration achieved is 20 mg, which turns out to be 5 liters. Assuming the water beaker to be plasma, these are the values that came out when we considered that all the drug is in plasma. But such is not the case.
Oh, what happens then?
Drug is distributed to all the compartments of the body. Let's consider the IV route of drug administration. When the drug is injected into the blood vessel or intravascular compartment, a part of it travels to the extracellular or interstitial compartment and also gets distributed intracellularly into body tissues and organs. Therefore, all the drug that's injected does not remain in the intravascular compartment or plasma. Assuming that we gave 100 mg of a drug, after all this, we withdrew the blood and checked the concentration of free drug in the plasma that came out to be 40 mg. That means 60 mg of the total drug is distributed into the tissues and only 40 mg of the drug is available in the plasma. Henceforth, the plasma concentration in this case would be 40 divided by 5, that is 8 mg per liter. And the volume of distribution will be total drug administered, that is 100 mg upon the plasma concentration, that is 8 mg. That turns out to be 12.5 liters. By comparing both the examples, in the first case we have less volume of distribution, therefore more drug stays in plasma. And in this case, the volume of distribution is more, hence less drug stays in plasma. That means more is distributed to the tissues.
Oh, so what's the clinical significance of knowing volume of distribution?
If you know a drug has more VD, you will need to give a higher dose of a drug to achieve a therapeutic concentration. Conversely, if a drug has less VD, more drug will be present in the plasma to produce therapeutic effect. Hence, less dose of drug will be needed in this case. In conclusion, VD helps us determine the dose of the drug.
Oh, okay. But how does it work in clinics and hospitals?
Let's take an example of a drug, chloroquine, which is primarily used to prevent and treat malaria.
Oh, well, which is also Donald Trump's favorite coronavirus.
Well, anyways, so chloroquine has the volume of distribution of 15,000 liters.
Kinda scary, right?
It has a tendency to distribute into the body's fat and is metabolized quite quickly by the liver. Let's say 100 mg of drug is enough to kill the parasite present in the red blood cells. But this 100 mg gets distributed to fat cells around the body. Therefore, you increase the dose to 200 mg. again it gets distributed to the adipose tissues. So you keep on increasing the dose until fat cells can't accommodate the drug. Assuming that you gave 1000 mg or 1 gram of the drug, so 900 mg goes to the extravascular tissue and 100 mg stays unbound in the plasma to kill the parasite. This initial high dose needed to start the therapeutic effect is known as loading dose. In our case, it is 1 gram. Therefore, loading dose depends upon volume of distribution, which is 1000 mg, and also on the target plasma concentration, which is 100 mg. Now, let's say after 7 hours, half of the drug is metabolized in the liver, and the dose reduces to 50 mg. In order to keep the medication working, we'll have to give the drug to increase its concentration to 100 mg in plasma. This dose of the drug that's given after 7 hours is known as maintenance dose. Hence, maintenance dose depends upon clearance, which is a measure of metabolism of a drug, and also upon the target plasma concentration. We will look into the details of clearance in my next video on pharmacokinetics of metabolism. We just talked so much about volume of distribution. That volume of distribution is different for different drugs. That is, drugs get distributed into the body tissues variably.
But why? What are the factors that determines a drug's VD?
The first one is lipid solubility. Lipid solubility is directly proportional to the volume of distribution. If a drug is more lipid soluble, it can easily cross the cell membrane and accumulate intracellularly. The second one is the fat content of the body.
This is kind of interesting one.
Because if a person is obese, the dose of drug required for him or her will be higher, especially if the drug is lipid soluble and has the tendency to distribute into body's adipose tissues. So, we can say that with increase in fat content, the volume of distribution increases. Conversely, athletes has lower volume of distribution. The volume of distribution in females is more than in males because there is more fat content in females, and the volume of distribution increases with age. So we saw that volume of distribution is directly proportional to the lipid solubility and fat content of the body. The third parameter on which VD depends is protein binding. The VD is inversely proportional to protein binding.
Why?
Because when the drug is protein bound, it remains in the intravascular compartment and hence cannot be distributed to the tissues. Therefore, volume of distribution is low. The two major plasma proteins to which these drugs bind are albumin, which we all are very much familiar with, and alpha-acidic glycoprotein. Albumin binds to acidic drugs, and alpha-acidic glycoprotein binds to basic drugs. The examples of the drug that bind to albumin are antibiotics such as penicillin, tetracycline, or sulfonamides, warfarin, and benzodiazepines. The examples of the basic drugs include the CNS drugs like tricyclic antidepressants and opioids, the antiarrhythmic drugs that are beta blockers, amiodarone, and lidocaine. Last parameter on which the volume of distribution depends is tissue binding. Tissue binding is directly proportional to volume of distribution. Depends upon presence of tissue-specific transporters. An example is of digoxin. Digoxin has a very high affinity to skeletal muscles. So, the loading dose is calculated on the basis of lean body mass and not the whole body mass. Another important clinical concept I'd like to discuss here is of dialysis. This removes the drug or nitrogenous waste from plasma. Now, let's say a patient came to your clinic with a drug poisoning. Hemodialysis will not be effective in the individual if the drug has High volume of distribution because drug is present in other tissues. Therefore, the plasma concentration of the drug will be low. Also, if a drug has high plasma protein binding, because dialysis does not remove proteins from the blood.
Are we done?
Hell yes! That's all for today's tutorial. I hope you enjoyed listening to me. If you did, please click on like, subscribe and share. Click on the notification bell down below so that you can get the updates as soon as I post the new tutorials.
Bye-bye for now.